Hello, this is video 45. In this video, I'm going to talk about conservation of energy with friction. So it's a continuation of what we've been doing with conservation of energy, but now we're not neglecting the friction that's in the problem. So we're going to solve these problems just the same way, but you can see in our equation for conservation of energy, we have an extra term, the work done by non-conservative forces. So in our case, it's just going to be friction is going to be our only non-conservative force. So what we're saying here is that we have our initial mechanical energy, the sum of the kinetic and potential energies, and then friction does some kind of work, and then we're left with some kind of final mechanical energy. So since we're only going to be dealing with friction, we're going to simplify this equation. I know it looks like I've made it a lot more complicated, but the first three terms are what we saw in a previous video for the sum of all the initial energies. The last three terms are the mechanical energy at the end. And the only new thing here is that we have a term for the work done by friction, which is minus Fkd. So friction is doing negative work. That's why it's a negative. We learned that if the force is opposite the displacement, that it's negative work. Friction does negative work. So what this means is that we have some initial energy, but friction is causing us to lose some energy, and then we're left with the final energy. Now I've made a note here that the work done by friction is reducing the mechanical energy. That's what you can see here. We had some mechanical energy, but we lost some. But the total energy is always conserved because this is still conservation of energy. So you might think, well, okay, but you just said we lost some energy. Think about a good example. You're sliding down a slide and you're wearing shorts, not pants, so your leg is rubbing against the slide. What do you feel? You feel like your leg is getting hot from the friction. So what's happening is that energy that of motion of you sliding down the slide is being converted to heat, which is a form of energy. So that's why we say energy is lost from the mechanical energy, but it's not lost from the world. The energy is converted to heat, which is then dissipated into the environment. So we can't recover it, right? It's not reusable. That heat energy doesn't get converted to some motion for us, right? It just gets into the environment. So we lose it from us, from our system, but it's not lost forever. It's not lost completely. So let's see how we use this equation. I have one example to do in this video. Example, aid incline with friction. A 50 kilogram skier with initial speed of 8 meters per second is coasting up a 2.5 meter high rise. So that's actually the height of the incline. It's not the length of the incline. Find a final speed at the top given that the kinetic friction force between her and the snow is 32 newtons. So as she goes up this incline here, there's 32 newtons of friction force. Assume a straight line path up the incline, and that's just so that we'll be able to make a triangle here. And we want to find her speed right here when she gets to the top. So we're not worried about what happens over here, just the motion up the incline here. So let's write down the conservation of energy equation. Initial kinetic energy plus initial gravitational potential energy minus the work done by the friction force equals the final mechanical energy, kinetic energy final, plus potential energy final. Let's see if we can cross anything that's equal to 0. Well, this time the starting height is 0, so don't get used to the final height always being 0 like in our previous example. This time the initial height is 0. That's the lowest point in the problem, so she does not have any gravitational potential energy initial. Can we cross out the kinetic energy at the end? No, we cannot, because she has some final speed. She also has some final height. We can't cross that out. Can we cross the initial kinetic energy like we have been doing in a lot of problems? No, we cannot, right? She has an initial speed. She's not starting from rest. if she were starting from rest, she would not be able to make it up the incline. She has to have some speed to go up. So this is the only thing that we can cross out in this case. So we can write out the rest of the terms. 1/2 mv initial squared minus friction force times distance. The kinetic friction force is defined as mu times n. Oh, but this time we're given the friction force, so we don't have to write it out. I simplified the problem a little bit by giving that friction force. 1/2 mv final squared plus mgy final. So all that's left to do is make sure that we have all of the information that we need and then solve for mv final. So let's make sure, let me go ahead and write down my givens here just because there will be a lot of numbers. So the mass is 50 kilograms. The initial speed, I'm just going in order through all the terms that I need here. The initial speed is 8 meters per second. Friction force is 32 newtons. The distance is this right here, this distance up the incline. This distance is always the distance through which that friction force is acting. So we're not given that because we're given the height and the angle. So we actually have to solve for the distance. So I'll do that right up here. We know that we're given the opposite and we're looking for the hypotenuse. We can use a sine of 35 equal to the opposite over the hypotenuse, equal to 2.5, the opposite over the hypotenuse, which is d. So d, if we solve for it, we just multiply both sides by d and then divide by sine of 35. We'll get 2.5 divided by sine of 35 degrees for d. So make sure to go through that algebra there. I got 4.36, but again, don't round until the very end. I just have to round here on this paper. So we have the mass. V final is what we're looking for. G is 9.8. Y final, the final height, is the given 2.5 meters. So when there's a lot of numbers, I go ahead and write them down so that we don't get confused. So now we can scroll down here and we can do the algebra to solve for V final. So I'm going to subtract mgy final from both sides. So I have 1/2 mv initial squared minus the friction force minus the final potential energy equals 1/2 mv final squared. And then to get v final by itself, I need to multiply by 2 and divide by m to get rid of the coefficient here. Multiply both sides by 2 over m. So I'm showing all the steps here. And you can just scroll to the end if you don't need to see all the steps. And so, right, when I multiplied the right side by 2 over m, you can see that it canceled out the 2 and the m here to leave us with just v final squared on the right hand side. So I multiplied both sides by that 2 over m. And then I just have to take the square root to get vf by itself. Take the square root of both sides. So there are a lot of numbers to plug in. This is going to give us vf over here. Plug in all those numbers. Go ahead and do that. Square root of 2 over 50 times 1/2 times 50 times 8 squared minus 32 times 4.36 minus 50 times 9.8 times 2.5. So I wanted to do a problem like this because sometimes in the homework problems you do have extra numbers to plug in. So plug all of that in and I got 3.07 meters per second. That's our final speed. So just to recap, when you have friction in a problem, you can still use conservation of energy. Just think to yourself, is my speed changing and height changing, and or is there a spring? It's a good candidate for conservation of energy. And just make sure to not get too used to always crossing out that initial kinetic energy. you're not always starting from rest. You really have to look at the picture and identify all the givens, plug them in, cross out what's equal to 0, and solve for your unknown.